Axom is a computer science infrastructure library that we use for our simulation codes. This tutorial is going to be on an application that we use in our simulation codes to initialize multi-material simulations, specifically when we have complicated shapes that we want to get into our simulations. We call that shaping them in because we have shapes that we're trying to get into our simulations. We represent these shapes inside the simulations using fields called volume fractions. I'll go into all of those details. But for the purpose of this tutorial, we're using it as a way to talk about all of the infrastructure that we've built up in Axom to support this application. So there's 5 lessons that we'll go through. The first one is sort of a hello world. Let's build Axom and see what that looks like and just how it's configured. Then we will talk about 4 different components in Axom that lead up to this application that we're talking about. And I'll go through those details. So let's get started. Okay, so Axom is a modular collection of libraries. We call them components that provide infrastructure for building these large multiphysics simulations. We have a whole bunch of different components that do different things, dealing with data management and I/O, as well as computational geometry and logging and all sorts of other things that are useful for simulations. When we started this project about 10 years ago, we looked at our large simulation codes, and it turned out about 40-ish% of the lines of code in these multi-million lines of code simulation codes comprise computer science infrastructure that sort of every simulation tool needed to develop, but it wasn't the focus, and a lot of those things weren't tested in isolation. And by pulling out sort of the best practices in these libraries of the computer science infrastructure, we were able to sort of hone in on what is important for running these simulations from the computer science side, and how do we sort of define good interfaces and focus on performance and all of those other good things. So that was sort of the core of how Axom got started. The build system we developed for Axom became the BLT library, which we use in a lot of our codes at Livermore and is used outside of the lab. BLT is a CMake. It is a set of macros and other sort of best practices that we use for building CMake build systems for our codes, and it has a lot of nice features for running on our high performance computers. So let's talk about the shaping application, which is sort of what we're focusing on as a way of talking about the infrastructure in Axom. The idea is that we have a computational mesh composed of cells, and that mesh represents a bunch of different materials. So you could be simulating something where you have water and air and maybe some sort of other material, and you might be interested in how the materials relate to each other. But these materials are distributed in space. And the way we run these multi-material simulations is you loop through the different materials and you sort of advance their physical properties as the simulation moves. And when there's more than one material inside of a cell, we represent that using these fields called volume fractions. So this talk is sort of about how do we set up these volume fractions when the user has complicated boundary shapes for how they're set up. So the basic idea here is that we have a computational mesh And we represent that in this in-memory data store using a component called CIDR, Simulation Data Repository. We have input that describes our geometry, and then we want to sort of figure out what percentage of each volume of each cell is composed of each of the materials. So that's our shaping process. We're shaping these materials onto the mesh. We encode them in volume fractions, and then we store that as fields on top of the mesh. That's sort of what we're going for in this tutorial. And Axom, like I said, is composed of a lot of these different components. We're going to focus on these 4 components, but they use a bunch of the other components in Axom. And I'll go through the details as we go along. So I guess just to get our feet wet, let's actually dig into the code and see what it's like to build up this just sort of a hello world application. The tutorial branch isn't sort of baked into this image, so you have to build it yourself. So these are the steps to do that. Once you load your window, basically you want to check out the feature branch and then build the code using this configure line, and then go into the installation directory. Once you have that done, it should take about 5-ish minutes to build the code and get that all set up. Okay, so we're going to configure this part of the installation directory. We're in the shaping tutorial directory if you followed those directions I had before. So if we look, we have an examples directory, and inside of that is Axom, and inside of that is our shaping tutorial directory. Okay, so if you're following along, we should be in. Is the screen big enough? Should I make it 1 notch bigger? Maybe I'll do that. There we go. Okay, so we're in our shaping tutorial example, shaping tutorial directory, and we're following along these directions here. So I'm going to make a build directory and go into it. And then I'm going to use CMake to configure that. Actually, I'm going to change my directory so it's looking in the right place. So Axom repo, shaping tutorial, samples, Axom, shaping tutorial. Perfect. Okay, so I'm in my tutorial directory. I've configured CMake in the build directory, and I'm going to build the code. And while I do, I want to show this host config. So the idea is that we configured Axom and installed it. And instead of like configuring this tutorial with all of the different flags and compilers and options that we want to build it with, we've saved them into this CMake file that we call a host config, and it just has all of the instructions for building the code, all of the CMake configure options. So our compiler is here, the flags we're building with, and just other things. We're using C++ 17. We've shut off the documents and examples and etc. So Now, if we look at the way, if we haven't installed Axom and we want to use it, everything is set up to use all the dependencies that we've configured Axom with. So all we have to call in CMake is find dependency Axom, and we pointed to Axom's exports, and then we are good to go. So it's building our examples right now. Should not take too long. Maybe another half minute or so. Are there any questions while we're waiting for this to finish building? Okay, so it looks like it's almost done. Let's look at our first example while we're waiting for that to finish. So this example includes the Axom config.hpp file. That includes all of the CMake defines that we're using um, in our Axom configuration. I'll show what that looks like in a second. Then the only thing we're doing in this example is calling Axom get version and then Axom about, which just prints some information. So if we run that, we'll call bin lesson 0, check Axom configuration. And that tells us we're using Axom version 0.11, and it's using C++17. Our Axom is configured with all of these components enabled, core, bump, inlet, etc. We have a bunch of built-in dependencies that we're using. CLI 11 is for parsing command line input. FMT is for string formatting. SOL is a Lua library. And sparse hash is a hash library that we use in some of the parts of Axom. We also have a bunch of external dependencies. So we've configured with Adiac and Caliper for getting performance data. There was a Caliper tutorial earlier in the series that you could watch the recording of, or hopefully you attended it. There's also some other libraries, Conduit, HDF5. MFEM is a finite element library that deals with high order finite elements. Raj and Umpire are performance portability libraries. So a lot of these are part of Livermore's open source software that we've had tutorials on in the series. And Axom is sort of built on top of a bunch of these components. So returning back to our tutorial for a second, let's see, I think that covers lesson 0. So this is our about world where we configured CMake and we built the code and we ran this sort of hello world that just tells us about Axom. I did want to show what that config.hpp looks like. So let me just find it directly. I think it's here. So it's in the include directory for our installation, and it's there. So this has our version information for Axom, some paths to where it was built, and then it tells us which of our programming models were built with. So this configuration is using CUDA. The node you're on has CUDA support and an NVIDIA GPU. This tutorial is not going to focus on GPU aspects. We have a different tutorial that focuses on using Axom with different programming models, with CPU support, with GPU support, and sort of the benefits you can get from running on a GPU when you have them. That was last year's tutorial, and there's a recording on the HPC IC link that Tara posted earlier if you want to watch last year's tutorial. And it's also in the Axom code if you want to run that tutorial yourself. We in this config.h, we also list all of the dependencies that we're configured with. Some of the ones we're not configured with are also here, and you can see which ones this particular instance is not configured against. And then these are all the Axom components that are enabled. This configuration has them all on. And then there's some other stuff in there. So it can be useful to look in this config file to see how Axom was configured. And when you're writing code in Axom that conditionally depends on some dependencies or components, you include this config.hpp, and then you have access to all of these defines. So let's go back to our lesson. So that's the end of lesson 0. Does anyone have questions? Or should I continue to lesson 1? Okay, I will continue to lesson 1 then. Excellent. So we're well along our way. We have our installed Axom. We have our everything is built. So now we're all set to get into our actual application. So for this first lesson, what we're trying to do is set up a 2D Cartesian mesh. So the user will provide us with some metadata associated with a 2D Cartesian mesh, and then we'll generate that mesh and be able to visualize it. So we're going to store this mesh inside of the Axom component called CIDR, which is the simulation data repository component. I'll go into some of those details, but the only thing you need to know about Cartesian meshes for the purposes of this tutorial is that they're defined in space in some sort of bounding box. So we need to know the lower left corner of the bounding box and the upper right corner. And we also need to know the resolution, which is like how many cells do we have in each dimension. So in this case, our lower left corner is 50, 50 in the X and Y coordinates, and our upper right corner is 350, 350. So the bounding box has a span of 300 width and 300 height. And our resolution here is 8. So there's 8 cells in each dimension, X and Y. So this lesson is focusing on the CIDR component. CIDR is sort of built around the metaphor of similar to like a file system. So you have directories and files in a file system. In CIDR, we have groups, which are sort of akin to directories, and we have views, which are sort of similar to files in our file system. So that those are sort of the main metaphors. These groups and views all live inside of a top-level container called a data store. The data store also has buffers, which are sort of arrays of data, just sort of blocks of data that we're putting stuff into. So CIDR can manage its own memory. You can allocate a buffer and then use that in a view. And we can also add attributes to our views that give a little more metadata to it. So for this example, we're going to have a very simple struct for our 2D mesh metadata. We're going to store the minimum X and Y coordinates, the maximum X and Y coordinates, and the resolution as 2 integers. So this is what it would look like in CIDR code to set up this mesh metadata using the input data that we just described right here. You create a group called mesh for sort of the root of our mesh metadata. Inside of that, we create another group for the bounding box minimums. Slashes are sort of hierarchical. So when we call create group bounding box slash min, it creates a group called bounding box, and then inside of it, it has a child called min. Inside of that bounding box min group, we're adding a scalar value for the x coordinate and the y coordinate of the min. Then we're doing something similar for the max. So we have the max x and y coordinate. And then we do the same for the resolution. So the resolution is two integers, x and y. Once we've run this code, our CIDR hierarchy looks sort of like this. We have a hierarchical structure with mesh. Underneath it is a group called bounding box. Inside of it is a group called min, which has an x and y coordinate, similar for the bounding box max and the resolution. So let's see. So we have an example for the mesh metadata where we can supply those values and set up our mesh. So let me run that. I'm going to go back here, open the terminal with my control tick, I guess, the thing above tab. So we're here. We're going to run bin lesson 1. If we just do -h, that tells us what our options are. So we can supply a min XY, max XY resolution. I'll get to that option later. If we run it with no options, then we get the default. In this case, it's 0, 0, and 10, 20. We could supply our, let's see, min X is 5 and max X is, I don't know, 15. And res X is 10 and res Y is 10. And of course I got something wrong. What did I get wrong? I spelled it wrong. Okay, there we go. And lo and behold, it sets up that metadata for us like we were expecting. I didn't add any sort of validation here. So if you set the min x to like 50 and the max x to 15, it'll just take those values. We could add that validation, but the next lesson will show a better way to do that. Okay, so I'm not going to go through this challenge right now, but the way we set this up was that x and y are scalar values. There's just one value for x and one value for y. A different way to set up this hierarchy might be to use an array for the mins and an array for the maxes and an array for the resolutions instead of individual values. So here to set up individual values, we did create view scalar. So we added a scalar value, which is just one entry. We could have set this up to allocate arrays. In this case, it's an array of size 2 of type double. And then we could fill those arrays. So that would be another equally good way to do this. And maybe the preferred way of thinking ahead if we were thinking maybe this would be also something that should work for 3D Cartesian meshes. Okay, so at this point we've provided simple metadata. Brian, can you help with that issue? It's for the other tutorial. The radius tutorial was last year's tutorial, and that talks about loading meshes. For this year, we're looking at the shaping tutorial. Let me just type that in. Yeah. Okay, great. Thanks, Brian. Okay, so going back to our tutorial, we supplied the bounding box information and the resolution. So here we're going to convert this into a mesh format that we can use in our software or in our visualization tools. This is following the conduit mesh blueprint conventions, which sort of defines different sort of metadata associated with meshes and allows you to represent the structure of these meshes, and then we could pass them around in simulations. So it's a very similar representation to what we provided, but it's a little different. So we're storing the bounding box and the resolution of the mesh, like the number of cells, as well as sort of the lower left corner, upper right corner. In this mesh blueprint convention, it stores the origin in the same way. That's the lower left corner, xmin and ymin. Instead of storing the resolution, it stores the number of grid points in each dimension. So the number of grid, so like we're storing the cells, and it's storing sort of the grid points, the lines bounding them. So there's one more grid point in each dimension than cell. So it's a simple transformation. We just add one to the x and y for the dimensions. And then the last thing is, instead of storing the upper right corner, it stores the spacing between each grid point. So there's also a pretty simple transformation there. It's the x max minus x min, and that whole thing divided by the resolution. So after that pretty simple transformation, we can convert our 2D mesh metadata thing into this conduit mesh blueprint using a uniform mesh. And this is what it would look like in YAML. We could do that for our input. So we're running our lesson 1 again, and now we use, oh, I forgot what it was. It was, oh, I think it was just a toggle whether we're outputting to blueprint or not. So here I'm turning that on. We did that, and is this gonna work? No. Okay, that didn't work, but I could load that. So that generates this mesh blueprint that I just mentioned. We have all of that stuff. It also generates this extra thing that I don't really want to go into here called the blueprint index, but essentially that's used inside of our visualization tool visit to be able to load things on multi-domains at the same time and not have to load all the fields at once. So once we have that blueprint representation, we can load that into visit, and it generates this mesh that we wanted. Let's look at the code for that really quickly, just to see that it's as straightforward as we said. So here's that struct we were talking about. Here's that function that generates our CIDR hierarchy, create group, adds the bounding box min and max and resolution. Why should we choose Axom over other tools? That's a great question. It depends what other tools you're interested in using. So Axom is set up to sort of use best practices from our simulation codes at Lawrence Livermore for helping with computer science infrastructure. So I guess you should use Axom if you're interested in setting up a simulation code without wanting to focus on all of the details of how to do the computer science infrastructure for your simulation. If you want to sort of just use tools that are already exist and are well tested and work on various performance portability sort of platforms, it's probably a longer question, but maybe let's revisit that after. Yeah, maybe let's revisit that after the tutorial when we've focused more on some of the details of Axom. Okay, thanks. So yeah, this is how we set up the CIDR hierarchy. I have a function in here to verify that all the metadata we expect is there. It's mostly a way of just sort of seeing how to use CIDR. One nice thing here. Oh, never mind. I'm not using it. If you want to look at all the groups inside of a group, we have an iterator interface, so it uses like C++'s range 4 syntax, but I thought I was using it, but it looks like I'm not here. But it does exist. And here's that function to convert from our metadata thing from our CIDR group to this blueprint schema. This first half is just pulling. Okay, this first half is just pulling information out of CIDR, and then the second half is applying those transforms we were talking about. And then we could just, Conduit has built-in ways of saving blueprint meshes. So we call verify to make sure all the fields it expects are there, and then we save the mesh. Okay. Any questions on lesson 1, or should we move ahead to lesson 2? Okay, moving ahead to lesson 2. Yeah, thanks everyone for handling all the chat messages. Just to clarify a question that Charles had about, yeah, the image puts you in the wrong directory. It looks like we didn't update it from last year, so you need to change the folder and rebuild stuff. Okay, so lesson 2. So if you're following along, we just covered lesson 0, which was sort of our hello world, showing Axom about and how to configure Axom. Lesson 1 was about this mesh metadata thing where the user supplies some entries and we can create a very simple representation of a Cartesian mesh. Lesson 2 is about a better way for users to input their data. Instead of supplying every value on the command line, we'd like them to supply a file with all of those parameters. And not only that, we'd also like to validate the entries so that certain properties we're expecting in the data are automatically checked as we're parsing this input. So we're going to use the inlet component of Axom to do that. Inlet for like, data coming in. So let's see. So yeah, like I said, we instead of providing all of these parameters on the command line, we'd like the user to provide a schema for their data and be able to validate it. Inlet has a few key components. A container is sort of a hierarchical group of entries. A field is a single entry, like a native type, like int, double, bool, or string. And inlet also has these verifiers, which are lambdas that you can set to be able to verify that data matches the constraints that you expect. So here's a basic schema for our mesh metadata. Remember, we had a bounding box, which had a min and max in X and Y, and we had our resolution, which is an integer for X and an integer for Y. Okay. Thanks everyone again for helping with the questions as they come along in the chat. If you do have questions, please ask them in the chat, and people will help you get the right answers. Okay, so in inlet we say add struct to add a container, and then once we have this container, we can add fields like a double. We can add like a description string that says what the thing should be. It also has some basic validation options that you can add as you're going. So I've augmented this first example with some additional things. So as you're adding a struct, you can say required. And then when it's parsing, if that field is not there, it'll throw an error and say, hey, I was looking for a bounding box and it wasn't there. So it makes it pretty easy to say that some of the fields or structs are required. The default is that things are optional. So if it's not present, it won't throw an error. But if you say it's required, then it needs to be there. You could add other things like the range. So our resolution here, we're saying it has to be a positive number. It has to be greater than 0. A resolution of 0 would be problematic. So we're not going to allow that. And then we can add these verifiers. So for the bounding box, we want to say that if the user supplied a minimum value that was not less than the maximum value in each dimension, that would be an error also. So we don't want a Cartesian mesh that does not have a positive range in X or Y. So here we're grabbing the values of min X and max X, and similarly min Y and max Y. And then we emit a warning if the min X is greater than or equal to the max X. And then we return true if things are valid and false if they're invalid. Okay, so that's for defining the schema. Then inlet also makes it easy to initialize our structures from this data. So let's show a structure, like a C++ struct, and then how we construct it in inlet. So here's our example. We have our mesh metadata struct. It's inside of it, there's a bounding box with our 4 values, min X, min Y, max X, max Y, as well as 2 integer resolutions. And then inlet has this template thing called from inlet where you give it your type. And then inside of that, you construct your structures from the inlet data. So here we're just doing the simple thing of pulling the data out. So we grab the bounding box and then we get the min X, min Y, max X, max Y, and the resolutions, and then we return it. So this is what it would look like when you're using the code. You would give inlet your file. In this case, it's input.yaml. We define the schema, which is that function we showed above that defines the inlet structs and fields. We apply the schema to validate it, and we get an inlet container. And then we call this, we initialize our mesh metadata struct from that container. When we call get mesh metadata, it calls this from inlet class if it exists. So let's look at what that might look like. So bin lesson 2 validated inlet input, and we're going to give it our input. So I guess I should probably show that file. So that file has our bounding box and our min and max and our resolution. So if I, let's say, made the minimum greater than the maximum, so the minimum is 1,000 now and the maximum is 33, and tried to run that, it would complain and it would say invalid bounding box for X coordinate, 1,000 is greater than 33. Okay, that would be a problem. If we didn't give it a bounding box, let's say we made a mistake and said it was the, I don't know, bounding box, I'm spelling it wrong, and we tried to run it, it would also complain and it would say required container not specified mesh/bounding box. So it helps us give structured input in the right way. Notice that we added a dimension field here that wasn't in our schema. And it's okay with that because we didn't say that any extra information you provide is a problem. So it's only looking at the fields that we told it about. Um, are there any questions on that? Is there a schema definition somewhere? Yes. The schema definition, well, I showed a code snippet before, um, but our schema definition is in our define schema function that we defined. So you pass in a container and then you tell it what the schema should be. So we say there's a struct called bounding box. Inside of that struct, there's another struct called min. Inside of that, there's a double called x. So these are fields, x and y. Similarly, we have the max struct, which has an x and y. And then these were in the bounding box thing. And then we go back to the top level one, the mesh schema, and then we add the resolution x and y. Is that clear, James? For what the schema contain, it's basically structs of native types. So it's nested C++ structures of native types, I guess. Um, it's up to the user to define what's in there. So it could basically be integers, doubles, strings, and callback functions. This lesson isn't talking about callback functions, but that's also allowed. Does that answer your question, James? Okay, excellent. Yeah, so if you look at the code, it's sort of basically what I showed here. Um, okay, so that was sort of our basic inlet example, which matched our cider example. But now we're going to make it a little more interesting. We're going to add support for 3D Cartesian meshes in addition to 2D meshes. We're going to add support for different input languages. So instead of just YAML, we could also use Lua. Um, Inlet also supports JSON, but we're not going to show that in this lesson. We're going to add additional validation. So, for example, if we're a 2D mesh, then we're going to say it's not valid to have a Z coordinate. But if we're a 3D mesh, we're going to require a Z coordinate. And then we're going to add a little bit of extra details so it's easier to work with this. We're going to use Axom's bounding box primitive instead of extracting the min x and y and z explicitly from inlet. So let's look at this first thing. We can add a verifier to our top level inlet container that looks at the field bounding box min z, bounding box max z, and resolution z. And then we say if the dimension is 3, then it's a problem if the z coordinate's not there. But if the dimension is 2, then it's a problem if it is there. So it's relatively simple to add these extra constraints. I forgot to mention, we also added the dimension field, which is just an integer that can be 2 or 3. Let me show what that looks like. So this is our improved example. If we go to our schema, we added an integer field called dim, and we gave it a range of 2 or 3. So that means it could only be 2 or 3. If the user supplied a dimension of 4, that would be a problem. If they didn't supply a dimension, it would be a problem because we said it was required in this improved example. And yeah, okay, so there's the code we were talking about. Let's go back here. Inlet supports different input languages, JSON, YAML, and Lua. So here in our example, we added support for Lua. So we're checking just the extension. If the extension ends with YAML or YML, then we use our YAML reader, inlet YAML reader. If it ends with Lua, then we use our Lua reader. Lua is an optional dependency of Axom, so we have to check if Axom is using Lua before we could do that. So this Axom use Lua was in our config.hpp. Do I still have that loaded? I do. So we can see that Axom use Lua is on. Perfect. And then, so basically there's just one line of code that says use our Lua reader instead of our YAML reader. And then we parse it like always and just move on. Um, so with those extensions, we can have a 2D input, we can have a 3D YAML input, we can have a 3D Lua input. I didn't show what the 2D Lua would look like, but it would be the same, just 2 dimensions. Okay. So let's run our improved example. So that's been lesson 2 improved. And we can see that that takes an input. So we're going to take our input from lesson 2. We have input 2d.yaml. Let me make the screen slightly bigger so we can see that. There we go. So we have our 2D YAML input. We have our 3D YAML input. We have our 3D Lua input. Let me show what that Lua file looks like. Okay, so let's just show some of those validation things. So if we said the dimension is 4 and tried to use our 3D input, it would say given value 4, MeshDim did not meet range constraints. And now if we said it was 2 dimensions but gave it a z coordinate, it would similarly complain resolution z should not be provided when dimension is 2. So it makes it easier to express these constraints and to sort of define our input. I very much prefer this sort of input to command line input from the first example. Yeah, so any questions on that, or should we move on to the next lesson? Okay, if you do have questions, please ask them in the chat, and then we'll try to answer them. So now we're in lesson 3. Oh, there is a question. I don't think Axom, the question is Axom opinionated on where to add equations in code or comments? I don't think we're opinionated on either of those, but I'd love to hear more about that question. Okay, so we're in lesson 3. So we're for this lesson, we're going to table our mesh metadata and talk about a different use of clay. I'm sorry, a different use of inlet, which is which has its own schema for defining shapes that we're going to use for our shaping application. So that's in our clay component in Axom. So if you're looking at all of our components and their dependencies, we're sort of moving up the chain a bit. We first talked about cider, then we moved up to inlet, which uses cider. I don't know if I mentioned that, but inlet is built on top of cider. So when you load data, it stores it in cider. And then you could access it using standard cider APIs or the inlet API. Now we're moving up to the next sort of thing. We're using clay, which is built on top of inlet. So it allows us to define a schema for how we define our shapes, as well as other properties about shapes. So, where the shapes are located on disk and applying different transforms to scale and translate these shapes. We call those operators in clay. And there's some other stuff that I'll get to. let's see, the main ideas in clay is we have a shape set, which is a collection of shapes, and each of those shapes has a name, an associated material, which is also just a string, as well as the geometry associated with that shape, like file format, and the geometry is not stored in clay. It's we point to files that contain the geometry for the most part. And then there's also this notion of replacement rules, which I'll talk about, which is how the shapes interact with each other. When you add a new shape, which other existing materials does it replace or preserve? Okay, so the first question might be, why did we call this component clay? So um, it was called clay after a Swiss artist, a Swiss German artist named Paul Klee, who was known for his paintings with geometric shapes and abstract patterns. The word clay also sort of just the way we're pronouncing it, clay, sort of evokes the concept of modeling and shaping. So here are some of his paintings, and you can see how they're sort of like shapes, abstract shapes on top of other shapes. Okay, one of the concepts in clay is that we're separating the geometric data from the replacement rules. So the geometric data lives in files, and then the clay input defines which shapes we're using and how they lay on top of each other. So one idea might be we could separately evolve our shaping logic from our geometric logic. So here's sort of a toy example where we start with a simple shape for this X pattern or jack, as I called it, which is just two rectangles that are rotated, and maybe as we evolve our design, we decide to give it circular caps, and then just as extra circles, and then we decide, hey, maybe let's make those simpler shapes that combine the different things, and maybe we just have one contour in the end, not all these other things. So all of that stuff is separate from the logic of which shapes we're using and how they lay on top of each other. So we're separating the geometry from the specification. Clay currently supports a bunch of different file formats. We have STL triangle meshes. We support this C2C format, which is sort of internal to the lab. So if you're not running on Livermore computers, then you can't use the C2C format for the time being. We also support this MFEM format for defining contours, so like 2D splines, and this Pro-E format, which is an ASCII format for tetrahedral meshes. Here's an example of what an STL mesh might look like. Oh, that's interesting. That is different than it looked. I think I'll show it here. So this is an STL file of a tetrahedron. So it's four bases. The format itself looks like this. So it's just a collection of triangles defined explicitly by their vertices. GitHub has a nice STL renderer, which is, I guess, why I created that link. Let me go back. Okay, and this will come up later, so I'll just mention it now. Axom has a Python script that allows you to convert SVG files to the MFEM format. So you could define your contours in your favorite vector manipulation tool like Illustrator or Inkscape. My new favorite way of creating SVGs is to just ask ChatGPT to generate an SVG. It's a text format, so I have some examples that I created below. It worked pretty well. Okay, so On the geometry side, we have these operators that allow you to transform your data. So it's like affine transforms. We could scale our data. So here we're saying we're loading this contour and we're scaling it by a factor of 5 uniformly in all directions, dimensions. We can also convert units. So the user might provide a contour that's in millimeters, and then we tell it that we want to convert it to centimeters. So that will just multiply it by 10. We could rotate our geometry, we could translate our geometry. So it makes it relatively easy to specify these things. So that's on the geometry side. Then on the replacement rule side, we're laying down these materials on top of each other, and we want to specify how they overlay. So you might want to do that if you have like two materials and then you want to put something between them. You might expand your geometry so it doesn't have to be exact. Here, this green shape could be slightly bigger, and we'll just say, it goes underneath, but it doesn't go on top. You could put something behind materials. Here's an example of what that would look like. So is that going to get bigger? Yeah, there we go. So here we have a simple definition. I didn't spend time working on the geometry here, so just imagine these are wooden boats sitting on top of a terrain that has water, mud, and grass. If we put our top boat down, we say its material is wood. It just goes on top of all the materials that existed there. So by default, it replaces everything. We could specify an explicit list of things that it replaces and everything else it will not replace. So for this middle boat, we say it covers the brown mud and the green grass, but not the blue water. So here we said it replaces mud and grass, but water was not on that list, so it does not replace water. And you can also specify the opposite. It replaces mud, but it does not replace anything else. So here, I'm sorry, I said that wrong. It will only, it does not replace mud, but it replaces everything else. So here, it replaces the water and it replaces the grass, but it does not replace the mud. So there we go. So here's an example where we have an outer shell that's a unit circle that's scaled by a factor of 5. So that makes it a circle of radius 5. And then we could add something underneath it that adds something that is 25 millimeters, which is 2.5 centimeters. So we're replacing part of that outer shell with an inner ball. I have a figure of this in the next lesson. So yeah. Okay, so what does it look like to use the Clay API? So I showed what the Clay input looks like in YAML format right here. But what does it look like to use the Clay API? We can define a shape set, a Clay shape set. We then read it in using an input file name. This is the validation side. So when we're reading it in, it will throw an error if any of the validation is triggered, and then it'll tell you all the things that are wrong in your input if there's anything wrong. Otherwise, we could proceed. Here's another function that shows more of the Clay API. In this case, we're just printing out the data that was in the Clay file. I wanted to highlight a couple things. So in this first step, we want to just get the list of all the materials in our input. Let me highlight that so it's easier to see, maybe. So we have a vector of materials, and then we say for each shape in, okay, no, I read that wrong. Sorry about that. We're creating a vector of our materials, and we're defining it with a lambda that we're immediately calling. So this is just an easier way to write this. So we get a set of our materials for each shape in the collection, shapeset.getShapes. We just insert the shape.get material. So basically we're getting the name of the material and we're adding it to a set, and then we return it as a vector. So this is a unique sorted list of the materials. And then here, we're looping through the shapes and just printing out information about them. So for each shape in the shape set, we want to add its name, material, format, units, dimensions, and the list of materials it replaces. So shape.getName, shape.getMaterial. We can access the geometry from the shape. That's its own class in Clay. So from the geometry, we can get the format as well as some of its properties, like its units and dimensions. And yeah. Okay, so let's give an example of how you might use this, sort of a whimsical example. We're building up an ice cream cone, and our constraints are that we have a cone, we have an ice cream scoop, and we have sprinkles. And we want to say that the ice cream replaces the cone, and the sprinkles replace the ice cream, but they don't replace the background the um, or the cone. So we would want these sprinkles not to cover the cone. We would want them to only be on top of the ice cream. So I'll show what that looks like in the next lesson when we pull it all together and do our shaping. But for now, I just wanted to show how we would specify that in our Clay input. So we would say there's a background material. This is a special thing in Clay. We can say the format is none, and that means the user is providing the input. Essentially, we're just setting it all the material to background before we get started. Then we're adding a shape called Vanilla Scoop. Its material is ice cream. These materials are just strings, so we can call them whatever we want. So our material is called ice cream. It comes in a file called icecreamscoop.mesh. That's in the mfem format. We used our SVG to mfem script to generate that. So the ice cream will cover the background material. It replaces everything by default. Next, we're putting on sprinkle. So what we say is that the name is just arbitrary. We call them colorful sprinkles. Its material is sprinkles. And that comes in a file called icecreamsprinkles.mesh. And we say that it replaces ice cream. So this list of saying it replaces ice cream implies that we're not replacing the background. So this is only going to cover the ice cream, but not the background. Then we add our cone of material batter, and we say that it does not replace ice cream or sprinkles. So we're saying it will replace all materials except ice cream and sprinkles. So it will basically, go underneath those. Here is our script or here's how we set things up to call our SVG to mfem script. It relies on this SVG path tools Python library. So we're using a virtual environment to do that, to set that up. So we create our virtual environment, we add our requirements that adds the SVG path tools and all of its dependencies. We have a small patch that we needed to get this working. It's essentially one character. And then we can call SVG to contours. We take our SVG file as input and we generate a mesh file, like an mfem file as output. And then we could load those mfem meshes into our visit tool to be able to see what those look like. Here's just all three of them on top of each other, just looking at the contours. We have our cone, our scoop, and our sprinkles. Cool. So for this lesson, the code loads in and inlet file. I'm sorry, it loads in a clay file and it just gives you details about the shape. So when we call that on our ice cream.yaml, this is some sample output. It tells us these are all the materials in the problem. It's a 2D problem. There's 4 shapes. There's the background, its material, its format, things it replaces. Let's see, I could run that really quickly. So lesson 3 takes a file. So let's give it lesson 3 ice cream.yaml. There we go. So yeah, it just gives the output I mentioned. I don't, let's see if there's anything to look at in the code. It's probably worth just looking at these SVG files for a second. I generated this in Inkscape, but the data itself is just the, let me go back here. It's just one contour defined by like 2 straight line segments and a quadratic curve, and this top thing is just an ellipse. So you can see that there's just a single ellipse and a single path that's a couple of lines and a quadratic curve. And I think, oh, cool. Okay, so I have a way of visualizing these SVGs in VS Code also. So you can see that it's just those 2 contours. And then when we convert that to MPEM, do I have that here? No, I have that in the next lesson, so I could show that in the next lesson. Close that. If we look at, oh, maybe the only thing I didn't show was this function that given a shape, a clay shape, and the list of materials, it loops through the materials and checks if the shape replaces a material. So we just call shape.replaces material. And if it does, we add it to the list. And that was how we got this list of things that each shape replaces, materials each shape replaces. Okay, otherwise there's not too much in this app. So let's move on to, well, are there any questions before we move on to lesson 4? Our last lesson? Okay, if there are questions, please ask them in the chat and we'll address them. Okay, so now we're on lesson 4. So let me just give sort of a top level overview of where we are. We're working towards the shaping application. In lessons 1 and 2, we defined a way of giving input to define a Cartesian mesh, and with some properties we used, first we supplied the parameters ourselves, and then later we used this inlet schema to allow the user to give us a Lua file or a YAML file with all of those parameters. So that's for the computational mesh. In the last lesson, we had clay, which defined certain shapes. And now in this lesson, we're putting those 2 together, where the user's giving us one file that tells us details of our computational mesh, and another file that gives us the shapes that we're putting into that mesh. And then we're going to apply those shapes to our mesh to generate these volume fraction fields. And then that is our input to our multi-material simulations. We could also visualize those volume fraction fields in visualization software like Visit. I'll show some examples later, but there are algorithms that do the reverse of our shaping, which is given these volume fractions, it extracts an approximation of the geometry that is represented, and I'll show what that looks like. So in this lesson, we're focusing on the quest component of Axom. which is sort of a high-level component of Axom that deals with doing spatial queries on meshes composed of collections of primitives. Some examples are this in-out query, which is we have a point in space and some surface mesh that bounds a volume, and we want to determine if that point is inside the volume bound by that surface or if it's outside. So that requires, to do this efficiently, we require a spatial index to accelerate our query, and then we have to do some computational geometry to determine if the point is inside this shape or outside of it. We have other queries like the point location query, where the user provides us a point in space and a volumetric mesh, and we want to know which cell from that mesh contains the point. And if we can find a cell containing that point, what are the local coordinates of the point inside of that cell? We have other queries like isosurface extraction, so we can do marching cubes or something like that to extract a surface based on a field value. The distributed closest point query is also an interesting one. That's where we have two collections of primitives that are distributed across the MPI ranks in our problem. So we could be running this on, like 1,000 or, more MPI ranks. And we have a point set that's distributed in one way on those ranks and a different point set that's distributed in a different way. And for each point in the first set, we want to know what is the closest point in the other set. And it could live on a different MPI rank. So there's collective communication that we have to do to determine that. So these are some of the types of queries that are built into the Quest component. Often they rely on spatial indexes, and often they rely on our performance portability abstractions based on Raja and Umpire. We have a different tutorial on that in Axom. If you look at it's called the Radius tutorial that talks about some of these aspects. For the purpose of this talk, we're focusing on the shaping application, which is inside of Quest. There are two different ways that we support doing shaping operations. I didn't add pictures, that would have been helpful. One of them is an intersection-based shaping. So we have our cells from the computational mesh, and we have our shape, and we do a geometric intersection to find the volume of intersection between our computational cell and our shape. And then the volume fraction is the percentage of the cell that's covered. So for the intersection base, we're computing an actual volume, and then that tells us the percentage of the cell that's covered for the volume fraction. This lesson is focusing on a sample-based shaping where instead of finding the actual intersection volume, we're approximating it by sampling points in each cell, and we're determining if they're inside the shape or outside of the shape. And then given a collection of these samples, we can approximate the volume fraction for each cell. Within this sample-based shaping, we have two implementations. One is called the in-out octree, and we have a picture of that here, where we build a spatial index over the collection of cells in our shape, and then we label we label the blocks of our octree, based on whether the entire octree block is outside of our shape. In this case, it's light gray. If it's completely inside of our shape, so it's dark gray, or it's on the boundary of the shape, which is this medium color. And if it's on the boundary of the shape, we have to do some additional computational geometry. If our point is completely inside based on the color of the octree cell, or completely outside, then we know immediately if it's inside or outside. The in-out octree, the way it's currently implemented, it requires the input to be linear. a linear discretization, so line segments or triangles, and it has to be watertight. If our geometry does not match those constraints, if we have curves or if there are gaps or self-intersections in our geometry, we have a different approach that's more computationally intensive called the winding number approach, that's tolerant to those kind of defects. And it returns the number of times your shape wraps around your point. And if it wraps around completely, then you get like 1 or something close to 1, and you could round it. Otherwise, if it doesn't, if your point is outside, it'll be something like 0. So okay, so how does our shaping pipeline work? We loop through the shapes in our clay input, and then we apply this pipeline. So basically, we load the shape into memory. We apply any sort of transform from our shapes operators. If we need to, we discretize the shape. So if it's curves, we might approximate it by a collection of line segments. Then we prepare the shape query by loading some sort of spatial index. That could be the in-out octree that we talked about before. This next step is to run the shape query. So for each cell of our computational mesh, we query the spatial index and find all the candidates that might need to be tested, and then determine either the intersection volume or whether the points are inside or outside. Once we have all of those samples or volumes, we can apply our replacement rules. So that either updates the thing we just computed for our current shape, or it updates the volume fractions of the other shapes. If we replace some other shapes, we need to adjust those. Then we finalize the query, we restore memory, and then finally, after we've applied all of our shapes, we might need to do some final adjustments to our volume fractions. For example, in the sample-based shaping, we need to convert our samples into a field, the volume fraction field. Okay, so that's sort of a very high-level overview of our shaping pipeline. I'm going to go back to the first lesson to show a picture if people came late, because that might help. So the general idea is we have our clay input, we have our computational shape. For each shape, we load them in, we determine whether points are inside or outside, and we apply our replacement rules if we need to replace some of the materials. And then we end up with our final volume fractions as a field. So, okay, now I'm going back to lesson 4. Okay, so we talked about the shaping pipeline. Now we're talking about the loading in our computational mesh again. So we're going back to our example from lesson 2 using inlet. We have our bounding box min, or bounding box max, our resolution. For this application, we're going to provide some additional input. So add some parameters related to the shaping. So that's easy to add in our inlet schema. We could add a background material. The user can say, this is our background material. Let's initialize it and set it all to 1 before we start. We could set some other parameters like the sampling order, how many points we're going to sample from each for each computational cell. And then we could also set the method. In this case, by default, we're going to use the in-out octree, but the user can tell us that we're going to use the winding number approach. Let's see. So it's pretty easy to update our schema from before. Probably the more interesting update here is for the sampling method, where we could say its valid values are in, out, and winding. So if the user provided anything other than those 2 strings, it would throw an error and say, you gave me the wrong method. That's an invalid value. That it probably implies that there's a typo somewhere. And then the way we handle that is when the user gives us a sampling method, it's not required, but if they do give it to us, we get the string out of inlet. And then if it's in out, we use the enum value sampling method in out. If it's winding, we use the sampling method winding number, and then we continue on. Okay, given our Cartesian mesh input, in the first example, we created this mesh blueprint thing. In this example, we're going to create an MFEM mesh rather than a low order mesh blueprint because some of our applications require shaping onto high order meshes, and we use MFEM for that, the finite element library, to do that. Because we do this in a bunch of applications, we have just a built-in function in Axom, a utility function in Quest to make a Cartesian MFEM mesh. It takes the bounding box as well as the resolution, and this is the order of the mesh. So in this case, we're using a computational geometry primitive from our primal component for the bounding box. It basically just stores the minimum and maximum coordinates. It's templated on the dimension because our point type is templated. It's either 2D or 3D. Okay, and then we have this MFEM mesh, and we store it in CIDR using this class called MFEM CIDR data collection. It's a hierarchical way of storing our mesh. It follows the mesh blueprint format that we talked about in the first lesson, but it does it for high order meshes, high order MFEM meshes. So we have this MFEM CIDR data collection. Our example uses MPI. If the user runs with MPI, it will automatically distribute the mesh across the domains of the problem. And we tell it to use this material set, a mat set of the volume fractions. That way, when we visualize it, it's a different way of setting up our mesh blueprint so that we can visualize the volume fractions and apply material interface reconstruction to it. So, okay, now we have our examples. Here is our SVG input for a circle. It's just a format that tells us our circle has a center of 0, 0 and a radius of 1. This is what our unit circle SVG looks like. We can convert it to an MFEM mesh using this SVG to contours script that we talked about. This is what the MFEM format looks like after we've converted our circle. So it's a MFEM NURBS mesh. It has 2 elements. They're cubic NURBS, and those are the control points for the NURBS. So basically, you don't have to know the details of that, but it just converts it to an ASCII MFEM format, which we can use in our application. Here is that example we showed before of the 2 circles with scalings and unit conversions. So we have a background material called void. We have an outer shell, that's the unit circle scaled by 5 units. So that's this orange one here. It's a radius 5 circle. Then we have an inner ball where we take away part of it. So the background material was void. This inner ball is void. And it's going to be 2.5 centimeters. That's this magenta ring. So this is the clay input. It's just these 3 shapes. There's 2 materials, void, background, and the foreground is steel. The user is going to supply their Lua input for the mesh metadata. So it's a 2D mesh that goes from -6, -6 to +6, +6. The resolution of this mesh is 100 by 100. And we tell it the background material is void. That works with this format none thing to tell it to fill that in. And we're going to use the in-out sampling for this. And then this is what visit gives us for our volume fractions when it generates the. Oops, I lost it. Here we go. And we also have a script that takes. So when we run this, actually let me run this. So bin lesson 4. We need to give it the mesh metadata input. So that's in lesson 4. I think that's circle input. And then we give it our clay file, which is also in lesson 4. What did I call that? Circles.yaml. There we go. So it's creating a 2D Cartesian mesh of resolution 100 by 100, and the bounding box is -6, -6 to +6, +6. It's processing the shape background with format none, then the outer shell with format mfem, and the inner ball with format mfem, and it generates the volume fractions. That created this shaping. Here, let me. Okay, so that created this root file called shaping.root, as well as this directory called shaping, and inside of it is the HDF5 file that has our mesh and all of the fields. We also have this visit script to the image that you have has a copy of visit in it. So we're calling this visit script to generate a plot. I think, yeah, the only thing this guy needs is I have to copy that unit circle file to this directory to make this work. Okay, so I'm just copying that unit circle thing, and then I could run. I hope I get this right. Okay, visit is in the home Axom dev directory, and I'm calling the CLI version with our script. Our script is called visit plot circle. Okay, so that's loading the output of our shaping with the volume fractions, as well as our unit circle mfem mesh. It emits a warning about missing boundaries, but that's nothing to worry about. Saving the image, then it will exit. It generated this file called visit 000.ping. And there is the file that we just rendered, which looks pretty similar to the one that I showed. I tweaked it a little bit more than this one, but yeah. Okay, so that was our first example. Oh, thanks, Brad. If I ran from the lesson 4, oh, that's how you set it up. Okay, Brad ran the shaping example from lesson 4, and that's why the files were there already. I'll do that for the next example. Thanks, Brad. Okay, yeah, so we just ran our sampling shaper with our input files, the YAML and the Lua file. And we got that image. Here's our ice cream example revisited. I know all of you are at the edges of your seat to see what this is going to look like. So We have our YAML file that we talked about last time with the background, the vanilla scoop, the colorful sprinkles, and the batter cone with our replacement rules applied. Our input here is going to be a 2D mesh that goes from 0, 0 to 400, 500. Our resolution is going to be 400 by 1200. Our background material is air. And we're going to use the winding number approach here instead of the in-out octree. One of the shapes here has self-intersections, and a different shape has, well, actually, I don't know about the self-intersections, but two of the shapes have elements that overlap, which doesn't fit our in-out octree constraints. But it works with our winding number. So let me run it the way Brad suggested. So I'm going to go to lesson 4, and then oh, I see. Okay, so it's in our build directory, and it's lesson 4. Our mesh input is going to be something with ice cream metadata.lua, and our clay file is going to be ice cream.yaml. Because this one's a little larger and because it works with MPI, I'm going to run this using 8 ranks. Huh, I didn't try that in this image. And MPI run? NP? Is it that? There we go. I ran it on a different machine, which had a different command, but looks like it's working. So we're running this on 8 ranks. It's processing our background, processing our vanilla, our sprinkles, our cone. Now we have all the samples and it's generating volume fractions from the material. So it's generating a high order volume fraction field for each material. Almost done. This is where I can put in a plug for our performance portability stuff. This volume fraction thing uses a full matrix assembly on the CPU for our finite element mesh, which can be a little slow. But when we run this on the GPU, it's significantly faster. So it's almost there. While we're waiting, let me go back um, to the example. So our last example in this tutorial goes back to the namesake for our clay component. There's this painting of the heroic roses that Paul Klee had, and we were inspired to see if we could create some sort of representation using the clay component and our shaping. So I hope this works. Let's see. We have this in our Axom data repository, which is LNL Axom _data, which just has some of our examples. This is a more complicated example, so it's we have a bunch of different shapes. Where did that go? What just happened? There we go. Okay, so we have a bunch of different, like greenish brown 0 is of material greenish brown, and it uses the MFEM format. There's some replacement rules in here. lots of different files that are processed. So that's our heroic roses mfm.yaml. And here are all the mfm meshes associated with it. I'll just randomly click on one of them. A lot of these shapes are fairly simple. And then this is the result. It's our interpretation of the heroic roses using using a similar visit script to the one we showed above. Okay, so now that that is ready, what do I want to do? I want to find visit. And I want to plot ice cream, I think. Okay, so this is loading our shaping results with volume fractions in visit. It's a multi-domain rank. It was run on 8 ranks. And we're generating a few figures. Visit 0, 1, and 2. So well, let me go back here. Is it not loading? Okay, it didn't like my click, so let me do it this way. Okay, so that loads our ice cream figure. We could also show, this is that same figure, but we're also showing the contours of the sprinkles, and you could see which parts of the sprinkles replace the ice cream and which parts of the sprinkles did not replace the background and the cone. And then this one shows our domain decomposition. So this is showing the 8 ranks of the mesh and which ones were on which rank in our distributed representation. And I think I had, yeah, I forgot to click that. The inside scoop with extra sprinkles. We have those 2 figures showing those 2 things. Okay, so that wraps up our tutorial. In this lesson, we covered our shaping application, at least the sampling side of our shaping application. I didn't cover the intersection part of it. We defined our additional mesh metadata for the shaping parameters. We created a high order mfm mesh with it. And we demonstrated our shaping workflow. On MPI, we didn't show performance portability through like GPU abstractions. Some of our some of our shaping stuff works with GPU right now, and some of it is being ported as it and should be available in the next couple of weeks and months. So this tutorial used a lot of different components of Axom. We used Inlet and Clay and Quest. I didn't cover the computational geometry part, but we have spatial indexes in our spin component. We have computational geometry primitives in Primal. Core is sort of used throughout Axom and has a bunch of utilities as well as some GPU compatible standard containers. So we have Axom Array, which is compatible with standard vector but runs on GPUs. We have a new flat map that's a hash map that works on GPUs. So give it a look when you get a chance. I wanted to thank you all for your attention. Axom is a collaborative project. We're definitely interested in feedback from the community, contributions of code for bug fixes or things that are interesting to you. If you want to contribute them to Axom, we're happy to review it and hopefully get it integrated. We're also very interested in how you're using Axom in your workflow. So, reach out, let us know. We're, we're always happy to hear from our users.
Yeah, so I'm just trying to like I'm not as familiar with Axom. I'm just wondering how it would work for because you've done like so much work to integrate this with all of these other libraries, and it's like this wonderful conclusion to this tutorial series. But I was kind of wondering for so the world or the world in which I've stepped into is like multi-scale modeling of like tissue and organ systems. So I worked with a group that would simulate like a patch of lung tissue and then sort of interchange with blood vessels and other organ systems, and you could simulate infection progression. And so, but one of the issues with that is it's kind of an older code base. It's like 20 years old. It's meant for CPUs, right? And so, we can't run this on like lots and lots of data, or we can't take advantage of like GPU centric architectures. So I was just trying to understand like if you've had like any like applications for agent based models. I know we looked at a lot of static shapes, but you're introducing new shapes and new locations, and so yeah, I was just wondering like if you have like any analogous applications to something like that.
Um, Not directly. So the CIDR component that I talked about at the beginning, we use that pretty extensively to store like computational meshes and fields on meshes. And something I didn't focus on at all in this talk was that once all of our data is in CIDR, it's pretty easy to do checkpoints and restarts. That was sort of one of the first applications. So put all of your data in CIDR, and then you could save it out to disk really easily just by calling one function and load it back in. Um, so maybe that's a useful thing.
Oh, that is super useful. uh,
Yeah.
hmm.
And so one of the other things we do is transfer mesh data from one physics package to another physics package using CIDR. So if your data is just in CIDR, then you give it a group, and then the other physics package can pull out that data without having to know the specifics of like APIs of your different package. Like you can just use it as a container for this hierarchical data.
And so it's
Um,
even without serializing, you mean? Or so this is like
yeah,
kind of
without
like
serializing, it's in memory.
right?
You could either use CIDR for that or conduit directly. If you have a CIDR hierarchy, there's a function that just converts it to a conduit node if that's easier, or you can pass CIDR data.
Okay.
Um, we have,
Yeah.
yeah, I I heard something about agents. I don't know if this is related to what you're talking about, but we have a lot of computational geometry algorithms and spatial indexes in Axom. So if you're dealing with like lots of sort of data distributed, lots of like geometric data distributed across space, we have algorithms for doing efficient queries on those or computational geometry things. Maybe
Okay.
that's related, maybe not so much.
No, that's very helpful. So if one was to like try to write up a proposal, just for like an initial prototype um, of an application, like um, how do you have your users try to like is that something they just you know like is there any sort of like discussion or forum in which people tend to do that in?
Um, I don't know that it's come up too much. People have we have an email that is on our GitHub page, axom-dev@llnl.gov. So that's a way to reach out to our development team.
Okay.
Um, if, if you're interested.
Okay, yeah, that's awesome. Thank you.
Yeah, so there's a lot in Axom that I didn't get a chance to talk about in this tutorial. So we have, let's see, what's the best way to show this? I probably should have mentioned this in the talk, but we have user docs that let me show you where I got that. It was just on GitHub LNL Axom, and I clicked on this docs thing.
Right.
So that sort of talks about our various components and what's in them.
Okay.
So that might be a good place to look to see if you know what's relevant to your application. We designed Axom around a new simulation code that we were building up about 10 years ago.
Okay.
But it's gotten into a bunch of other codes at the lab. So the modular nature of Axom has made it easy to like adopt one piece without adopting like a full framework. So that might be helpful for your code, which is out there, has lived for a long time, but maybe you want to fix up pieces of it or like sort of modernize some pieces of it without like a wholesale refactor.
Okay. Um, okay. No, thank you. Yeah, that's my question.
Excellent. Well, I appreciate your interest and your questions. Brad was asking, is there a way to discuss via GitHub? I don't think we have a discussion page. I mean, you can open up an ish. Oh, we do have discussion. I don't know if we've used it. I guess you can post a discussion if you're interested, and
Okay.
we could interact with you that way.
Yeah. Okay. Sweet. Thank you.